Hey, three, two, one. Let's get complex today in this 2070 video. Alright, jump right in. Here's a matrix. Where are the eigenvalues? There. Let's go ahead and get the characteristic equation, subtract lambda off the diagonal, take its determinant. You will arrive at the formula. 0 is equal to lambda squared plus 1. So, in order to actually talk about the eigenvalues of this matrix, we gotta talk good old complex numbers. My favorite. Alright, so, broadly speaking, the complex numbers are a way of turning our good friend R2, the Euclidean space, the Euclidean plane, into a set that has both addition and multiplication. Obviously, elements of R2 we know how to add, it's done component-wise, but we don't have a method for actually multiplying those things. So the idea is that instead of viewing them as an ordered pair x and y, we will view them algebraically as x plus iy, where we're going to enforce that I, the imaginary unit, satisfies the rule that I squared is negative 1. Right. That, of course, makes I not a real number. Every real number squared is non-negative, so I squared being negative 1 ensures that that piece there is not a real number, and thus x plus iy is a new entity. And we relabel R2 as a fancy C and refer to it as the complex plane when we're taking this viewpoint. Alright, so now that we have complex numbers, what can we do with them? Obviously, our main goal is going to be I want to get the roots of polynomials with these, but for our eigenvalues that we want, we need a couple of other tools when it comes to the world of complex numbers. So, there are many such tools, and if you are so interested, I recommend you take Math 3650 here at Iowa State, or the equivalent complex variables course at your university, or just study complex numbers on your own. Because there are a lot of really great tools and a lot of interesting mathematics that come out of the complex numbers, and one such tool is the conjugate of a complex number, and that's a word that you may have encountered in math before, and perhaps with Calc 1 and taking limits involving square roots, and you notice that, hey, I changed a plus to a minus, and that's the same story here. So if I want to conjugate 3, a minus, for I replace the minus with a plus, or the plus with a minus, however you want to do. Note conjugation, while a simple algebraic maneuver, right? In fact, there's a geometric way of viewing this. It's reflecting across the x-axis. One of the powers of this is that it lets us detect when a complex number is actually a real number. So in particular, if a complex number coincides with its conjugate, well then a plus ib is equal to a minus ib, and solving for that will force b equaling 0, and so z itself has to be a real number. Pretty cool. Alright, so complex number actually being real, meaning that there is no complex piece, IB, associated with it, can only happen when you equal your conjugate. Probably going to make use of that. Alright. Now, there are a lot of things that conjugation does in terms of algebra. So again, note the complex plane has adding and multiplication associated with it. And a fun little calculation is this one right here. If I take the conjugate of a product, well, multiply it out, take the conjugate, this plus becomes a minus, and then note, hey, wait a minute there, that is equal to this, and there we see our favorite phrase in mathematics, the x of the y is the y of the x. Here we see the conjugate of a product is the product of the conjugates. Wonder if we're going to make use of this. Alright, now, when it comes to complex numbers, we can create matrices and vectors that contain them. Here is a 2x2 complex matrix. Note it has real numbers floating in it too. That's because, note, real numbers count as complex numbers. And note that I can conjugate this because, hey, the real numbers don't care about the conjugation, and the complex numbers switch from plus to minus. Pretty cool. And what's even cooler is that we know conjugation and multiplication behave, and in fact that carries over to matrix multiplication. So if I take a complex matrix and multiply it by a complex vector, conjugating that product is the same thing as conjugating the individual pieces and then performing the matrix multiplication. Wonder if we're going to use that. again, our main goal here is to talk eigenvalues, and specifically, if we have a complex eigenvalue of a real matrix, then for any eigenvector associated with lambda, we know that AV is equal to lambda V. So, that formula right there. Conjugating both sides, well, we know we can pull the conjugates apart. The matrix is real, so conjugating it doesn't do anything, and now we have found that if lambda is a complex eigenvalue of a real matrix, then its conjugate is also an eigenvalue, and furthermore, its eigenspace must consist of the conjugates of the original eigenvectors. So this actually reveals that if you're finding that your matrix has complex eigenvalues, it's actually a little bit easier to compute eigenspaces because you just need to figure out the complex eigenvalues and then only figure out one of the eigenspaces because the other eigenspace will simply just be the conjugate. So for example, here is a matrix 1, 2, -4, 5. Characteristic equation is easily found. Again, we've done this multiple times now, so we're hopefully pros at this. And one of my favorite things to always point out is that whenever a prime number shows up in a polynomial, pretty good chance you got complex eigenvalues. And indeed, the roots of this polynomial can be found by adhering to the good old quadratic formula and then just recognizing that the b squared minus 4ac can go negative now, and that the I plays the role there. But I have always found that the best way of finding complex roots is to do good old completing the square, a thing that everybody absolutely hates for some reason. But I'm here to convince you it's great, because if I want to get the roots of this polynomial, first of all, we note that this part is possible to be completed as a square, where this number I am getting by simply halving this. And now if I square this out, I'll see that I get a lambda squared minus 6 lambda plus 9, but I didn't have a plus 9, I had a plus 13. So to combat that, I need to introduce this minus 9. So this highlighted piece right here coincides with that piece right there. And then that cleans up. And now, note you've got this expression right here, and that is super easy to solve for, because if I subtract the 4 over, well, the only way -4 coincides with the square of this is if lambda minus 3 was plus or minus 2i. Take the square root of this and replace the minus with a plus or minus I. Beautiful. Then you had the 3 over. And in fact, in this original form right here, I didn't even have to do this derivation. I could just read off that I know the real part has to be 3, and the imaginary part of the complex number is the square root of 4 there. So, I think when it comes to finding the complex roots, completing the square is the way to go, because, as you see, you can get right here and then immediately read off the real and imaginary parts. And as previously noted, I only need to figure out the eigenspace for one of these, and typically you go for the positive one, because then the eigenspace for the other is found by simply looking at the conjugates. So, let's go ahead and get the eigenspace for 3 plus 2i. That means I need to subtract that off the diagonal, and the tricky thing that happens here with complex eigenvectors is that we know this matrix is not invertible. Now, at first glance, that might seem like a bold claim. It seems like those are two linearly independent columns, but they're really not. Unfortunately, complex multiplication has got some subtleties to it. But regardless, we can just focus in on one equation and solve for it, and get a relationship between the v1 and the v2. In this case, I chose the top one because, well, I could divide the 2 and it's nice and clean. Here, I'd have to divide out at -4, I'd get some fractions, and I'd rather not deal with that. Alright, and here I find that a basis for our complex eigenspace is 1 plus I. There we go. That's the basis for the eigenspace, and thus the conjugate has to be the basis for the conjugate eigenvalue. Beautiful. That easy. Alright, now you know how to deal with complex eigenvalues and complex eigenvectors. Now, there is a lot more to the story of the complex world of eigenvalues and eigenvectors, and we're not going to get any further than right here, but if you were so interested, feel free to investigate. Alright, and I'm out.